Okay, and here we're going to actually find the length of plane curves. Now, we know about the length of a straight line segment, but without calculus, we actually have no notion of the length of a general winding curve. And the idea of approximating the length of a curve running from point A to point B by subdividing the curve into many pieces and joining successive points of division by straight line segment dates back to the ancient Greeks. And actually Archimedes used this method to approximate the circumference of a circle by inscribing polygons. So the extension of the idea to a more general curve is shown here. Now, to get this formula, you can actually look in any calculus text to find this formula derived for curve length. But I'm going to just bypass the proof and give you the formula. So here it is. If a curve is defined by the parametric equations x equal f of t and y equal g of t, where t goes from A to B, and the derivatives of f and g are continuous, and also both not zero on the as t goes from A to B, and the curve is traversed exactly once as t increases from A to B, then the length of the curve, called arc length of the curve C, is given by the formula L for length is equal to the integral from A to B of the square root of f prime of t quantity squared plus g prime of t quantity squared dt. Or another way to say that is the integral from a to b of the square root of the derivative of x with respect to t quantity squared plus the derivative of y with respect to t quantity squared dt. So that's the formula we're going to use. So the first thing I'm going to do is I'm going to show you that the circumference of a circle with radius r is indeed 2 pi r. Now, you should know that a circle can be represented by the parametric curves x equal r cosine t and x equal r sine, y equals r sine t, not x, and y equals r sine t. Okay, so now if you go from 0 to 2 pi, if you let t go from 0 to 2 pi, then these parametric equations will draw the circle one time. So now, to get the formula, you saw up there what I need is I need to get the derivative of x with respect to t. So if I take the derivative of r cosine t with respect to t, I get minus r sine t. And then if I take the derivative of y equal r sine t with respect to t, I get the derivative y is r cosine t. So then if I do dx over dt squared plus dy over dt squared, that would simply mean I square this, so I get r squared sine squared t. Then I square this and I get r squared cosine squared t. And then I can factor the r squared out of that, and so I get r squared times sine squared plus cosine squared. Well, since sine squared plus cosine squared is 1, then that's just going to be r squared. I wanted to do that there and not actually do it in the integral. So using the formula, if I integrate from a to b, my a is actually going to be 0, t equals 0, and my b is going to be t equal 2 pi. And then the formula says we do the square root of this quantity. Now I've already figured out that the quantity in the radical is r squared, so we integrate the square root of r squared dt, and that's just r, so I integrate r dt from 0 to 2 pi. Now if you integrate r with respect to t, that's just going to give you rt, so rt from 0 to pi, and then if I apply the fundamental theorem of calculus, replace t with 2 pi and I get 2 pi r, replace t with 0 and I get 0, and so 2 pi r minus 0 is 2 pi r. And that actually is the formula for the circumference of a circle. Believe it or not, it really is. Okay, so now this next one, I'm going to find the length of this asteroid that's defined by x equal cosine cubed t, y equals sine cubed t, as t goes from 0 to 2 pi. Okay, so this one's a little more complicated, but here's the asteroid here, and the asteroid actually completes one branch as you go from 0 to pi over 2. So actually what I could do here is I could go from 0 to pi over 2. I don't know really which way it goes, but I'm going to say it goes from here to here, but it might go from here to here. But anyway, as t goes from 0 to pi over 2, it's going to complete one branch. So due to the symmetry, I can just find the length of one branch and then just multiply it by 4. So just remember that when I get ready to do the integration. Okay, now if I take the derivative of this with respect to t, then that's just going to be 3 cosine squared t times minus sine t. And then if I take the derivative of this with respect to t, that's going to be 3 sine squared cosine t. Okay, well then I have to take these and square them and then add them up to find out what goes in the radical when I get to the formula. So if I square this, I actually get 9 cosine fourth sine squared t. And then if I square this, I get 9 sine fourth cosine squared t. And now I can actually factor out a 9 out of each of these terms. And I can also factor out a cosine squared t out of each term, as well as a sine squared t out of each term. So if I factor cosine squared t and sine squared t out of each term, then that's just going to leave me with a cosine squared t and a sine squared t here. So I'm going to basically have sine squared t, should be a t right there. So I'm going to have sine squared t plus cosine squared t there, and we know that's 1. So the result is just going to be 9 cosine squared t sine squared t, and so that's what I'm going to put in the radical. So if I put this in the square root here, okay, now I went ahead, I actually skipped that step, but the integral would be the square root of this, okay, and the square root of this would simply be 3 cosine t sine t. So I've got 3 cosine t sine t. And remember, I said I was going to just integrate this from 0 to pi over 2 to get one branch, and then multiply it by 4 to get the sum of all the branches. So anyway, if you here I'm going to factor the 3 out. Let's see here what I'm going to do. Just a second here. Okay, I see what I was going to do here now. Okay, so I wanted this to be 2 sine t cosine t, because then I can use an identity. So let me just tell you what I did. What I did is I took the 3 out. So I put the 3 out here with the 4. And then I wanted a 2 in here. So I multiplied the inside by 2 and then the outside by a half. So that's where that 2 came from. Now the reason I wanted a 2 in here was because I know that 2 sine t cosine t can be written as sine of 2t. So that way that's easy for me to integrate. Now let's see, 3 times 4 divided by 2 is 6, so that's where the 6 came from. Okay, and now when you integrate this, you're actually going to get minus cosine 2t divided by 2. And so if you have 6 times minus cosine 2t divided by 2, that'll give you minus 3 cosine 2t. And then we're going to evaluate that from 0 to pi over 2. So I'll let you do that. It looks like I've got just minus 3 times negative 2, which is 6. So it looks like this, if you evaluate this from 0 to pi over 2, you're just going to get negative 2. And so, because let's say you would get the cosine of pi over 2 times 2, which is cosine of pi, and that I think is negative 1, and then cosine of 0 is 1, so you get negative 1 minus 1, which is negative 2. So yeah, you get negative 2 there, and minus 3 times negative 2 is 6. So the sum of all those branches adds up to 6 units. There's also a formula for if the curve is given to you in terms of just y equal f of x instead of the parametrization. And so that formula would be that the length would equal the integral from x equal a to x equal b times the square root of 1 plus dy over dx squared dx, or if you prefer, you can write it as the square root of 1 plus f prime of x quantity squared dx. So a simple example of this was to find the length of the curve of y equal x squared as x goes from 0 to 4. Basically, all you have to do is integrate from 0 to 4, and then the derivative of this would be 2x. So just plug 2x in here, and so you get the square root of 1 plus 4x squared. And so that's how you would set that up. Now that requires a special formula to solve, and I'm not really going to go look that up for now. So, but you could look up the formula and then you could evaluate that definite integral. Okay, so if you actually want to do this integral, I looked it up on a computer program, and it says the answer is 16.819, but I'm not going to actually go through and evaluate it. Okay, so the next one says find the length of the curve, this curve, on 0 to 2. Okay, this requires quite a bit of algebra, so I don't want to get bogged down in the algebra, but let me just tell you that if you take the derivative of this function, you're actually going to get 1/2 times e to the x minus e to the minus x, and then you're going to need to square this. So if you square this, you're actually going to get this expression, and then in the formula you're going to have to actually add 1 to that expression. So here I'm going to add 1 to the expression, and then I'm going to simplify it. So I've done some algebra here, and then I simplified it here, and I kept simplifying, and I finally got it into this form right here. This form right here. 1/2 e to the x plus e to the minus x quantity squared. So then when I take that and I put it in the square root, okay, when I take this and I put it in this square root and then take the square root of it, since this is squared, when I take the square root of it, I just get this expression not squared. And of course we're integrating from 0 to 2. And so to integrate this from 0 to 2, you can do that. You're just going to get 1/2 e to the x minus e to the minus x, and then evaluate it from 0 to 2. So you plug 2 in everywhere there's an x, then you plug 0 in wherever there's an x, and of course you take the difference of these because you're applying the fundamental theorem of calculus. And the answer I got was, the exact answer was 1/2 times e squared plus e to the negative 2. And that's the exact answer. If you want an approximation, then you'll have to get a calculator. Okay, I'm going to just show you this real quick, and then I'm going to finish this on another video. Let's say you want to find the length of y equals x to the 2/3 from x equals 0 to x equals 8. That would be from y equals 0 to y equals 4, by the way. Okay, so it turns out that the derivative of y with respect to x is actually not differentiable at x equals 0. So what we could do is we could use another formula, this formula up here, where we integrate along the y-axis. So if you use that formula, then what you would do is you would solve for x in terms of y, and then you would take the derivative of x with respect to y, and so that would give me 3/2 y to the 1/2. And then I would just have integrate from c to d, which would be from 0 to 4 on the y-axis. So I integrate from 0 to 4 on the y-axis times the square root of 1 plus the dx over dy quantity squared. So I put that in there, and from there you should be able to take it and finish it. So if you need to, freeze the video and then just kind of work your way through the rest of the problem here. And you can see I kind of got a real weird number here, but that's the exact value. If you want to know the approximation for that, then you can just grab a calculator and go to town with it. Okay, so I'll do a couple more examples for the lengths of curves in one more video.